Okay, welcome to Robotics 1. Today we start this new chapter which is on the kinematics of serial robots. So what do we mean by kinematics? Kinematics is the study of position, velocity, and acceleration of uh, robot links. What do we mean by a serial robot? In the case of a serial robot, you have the links in series. So you have a ground link, you have one link that is attached to the ground, you have one more link, and maybe at the end, you have some sort of a gripper. So you have a ground link. This is the first link. This is the second link. And this is called as end effector. Now these links are attached to each other by means of joints. So in this particular robot case, this is a hinge. You have a hinge between the ground link and link number 1. You have another hinge between the link number 2 and link number 3. And then you have the third hinge in link number 2 and the end effector. Now, we are going to talk about different ways the velocity, position, and acceleration can be studied in the case of serial robots. As you know, velocity is the derivative of position. Acceleration is equal to derivative of velocity. And does anyone know what is the derivative of acceleration?
Jerk?
Correct. Oh, don't call me jerk. I'm just kidding. So you have velocity, uh, acceleration, and jerk. Now, this chapter talk about vectors, projections of vectors, transformations. So what I'm gonna do is I'm gonna start from the very beginning, and I would start with the definition of vector. But just to give you an idea where we are going with all this material. So we are going to look at analysis of open loop mechanisms. So mechanisms is the assembly of linkages that are allowed or that are formed to get some functionality output. So for an example, you could have a mechanism, something like a 4-bar mechanism that allows you to transmit motion from the link number 2, which is the crank, to the rocker arm. Or you could have an open loop chain type of mechanism, wherein think about this, that this is the first link of the robot, then you have the second link of the robot, and you have the third link of the robot. So closed loop mechanisms, the loop is closed. So what do I mean by loop closed? Think about it. I can represent each link of the mechanism as a vector. So I want you to think about this vectorial representation. So the loop closure equation O1A please note that this vector starts at O1, ends at A. So starts at O1, ends at A, plus the second vector that starts at A, ends at B, plus the third vector that starts at B, ends at O2, and then you have the fourth vector which starts at O2 and ends at O1. So this is called as the loop closure equation. So this is loop closure. But in the case of open loop mechanism, we do not have the close. The loop doesn't close. In other words, we do not have a link that connects point C all the way to O1. That's why if you see, this is 1 degree of freedom mechanism. What it means is for particular value of theta 1, I'm gonna have a particular value of psi 1. The relationship between theta 1 and psi 1 has 1-to-1 correspondence. On the other hand, depending upon this angle theta 1, depending upon this angle theta 2, depending upon this angle theta 3, the position of point C could be anywhere in this planar space. So that is the difference between an open loop mechanism and a closed loop mechanism. Please note that this is a serial link, or this is also called as serial manipulator. Why is it called as the serial manipulator? Because all these links are in series. So we are going to take an example wherein the links are not in series, but they are in parallel. So this is called as a parallel mechanism. What you see here is you have this link, link number 1, you have this link, link number 2, you have 3, 4, 5, and 6, and these links attach the top plate, so top plate to the ground plate or the bottom plate. So this is the reason why this is called as the parallel manipulator or parallel mechanism. Depending upon the relative extensions of these 6 links, you could have different orientations. You could have, just to give an example, if you think about a 3-dimensional coordinate system, wherein this is X, this is Y, this is Z, you could have orientations about X, Y, and Z. So you could orient this platform the way you want based on the actuation of different manipulators. Now, one thing I want to discuss at this point is, let me introduce you the basic coordinate system. So I know most of you probably know this, but consider a coordinate system, a Cartesian coordinate system. You have X, Y, and you have Z. So if you discuss a motion or a position of a point P that is in this 3-dimensional coordinate system, you would specify the coordinate as, say, maybe 3, maybe 2, and 1. What does this tell me? This tells me if I'm at the origin O, and if I want to go to point P, if I'm at origin O, and if I want to go to point P, I need to travel 3 units in x direction, 2 units in y direction, and 1 unit in z direction. So if I draw a vector which is O to P, I'm starting from O going towards P. Let me introduce the concept of a unit vector. So unit vector, so you have concept of unit vector that indicates direction, not magnitude. Because the magnitude of the unit vector, as the word says, it's unity. So magnitude of the unit vector is 1. So I need to travel 3 I units. Then in y direction, I have j, and in z direction, I have k. So if I travel 1 unit in x direction, that simply means 1i. If I travel 2 units in y direction, that simply means 2j. If I travel 3 units in z direction, that means 3k. So what I'm going to do is I'm going to write this vectorial representation. O to P is nothing but 3i plus 2j plus 1k. So this vector OP is 3i plus 2j plus 1k. Now this can be represented something like this. Now I want you to represent this vector something like this. Check this out. I can say 3, 2, 1 multiplied by I, j, k. So this is a vector multiplication. So when I perform the multiplication, I get 3i plus 2j plus 1k, which is nothing but the way this vector OP is represented. One thing I want you to note that this vector OP is not a unit vector. OP is not a unit vector. Why is this not a unit vector? Because if I were to find out the magnitude of OP, the magnitude of OP is going to be 3 square plus 2 square plus 1 square, which is 9 plus 4, 13 plus 1, 14. So I have square root of 14, which is not equal to 1. That's why this is not a unit vector. Now what I want to do is, I want to find out the unit vector in the direction OP. So the question is, and I will write this question here. So the question is, what is unit vector in OP direction? And to find the unit vector in OP direction, I'm going to call it N, is the vector divided by the magnitude of the vector. So I take this vector 3i plus 2j plus 1k, and I divide it by square root of 14. Now you will see that now this vector n is a unit vector, and this only indicates the direction. Some of you may ask me, okay, that's fine, but what is the advantage of unit vector? Now, the advantage of unit vector is it shows you direction, which means, so if you want to go from point O to point P, think about point O is in this auditorium, point P is in library. So you can say, hey, go right 3 units, turn left 4 units, again turn right 1 unit, and you will get to library. Or if everything is clear, you would just orient that person in the direction of the library. And mind you, it's the direction. And ask him that, hey, you just walk straight by certain units, and then you would get to library. So in other words, I could say, if you could orient yourself in this direction, if you could orient yourself in this direction and hat, and then walk distance square root of 14, you would get to point P. So I could also rewrite this vector OP as square root of 14 n hat. That is perfectly valid definition of vector. Everyone understood what is the vector? So the key concepts based on this discussion, you should be able to understand. And I'm going to say key concepts is vector and then the concept of unit vector. Now, what I want to do is I want to discuss something else, which is very important, which is called as the projection of vectors. Or let's, and most of you have studied this all the way in EGR to 17, but let me discuss some of these concepts. So consider a coordinate system which is given as X and Y. Okay. And then again, I would say this is I, this is J. And I have a vector OP. This angle is theta. So what I want to do is, I want to find out the projection of this vector onto I or onto x-axis, and this is going to be, if this distance is, I'm going to call L, this is going to be L cosine theta. If I were to find out this projection, this is going to be L sine theta. So please understand, cosine theta I would represent as C theta, sine theta I would represent as S theta. So the projection of this vector onto x-axis is L cosine theta. Projection of this vector on y-axis is L sine theta. Just, and if you want to find out the total magnitude, you can square the projection, add them, and take the square root, and that will give you the overall magnitude. This logic can be extended into z dimension also. So if you have a vector that is in 3 dimensions, x, y, and z, in a sense you have i's, j's, and k's, then you can follow the same process and you should be able to get the same answers. But before we get into the details of that, what I want to do is, I want to denote these terms slightly differently. So I'm gonna say theta x is the angle with respect to x-axis. I'm gonna say theta y is angle with respect to y-axis. So if I write these angles down, so check this out. This is going to be my theta x, and this is going to be my theta y. So I could, in other words, write this something like, and I want to pay attention here, because even though it may look simple, there is a little complexity involved. So check this out. Px is the projection on x-axis. P is the projection on y-axis. So I can rewrite this vector OP as projection on x-axis multiplied by unit vector in I direction plus projection in y-axis multiplied by unit vector in j direction. Now what I'm going to do is, I'm going to rewrite Px as something like this. L cosine of theta x I plus L cosine of theta y g. Now something interesting just happened. Now what I have here is, I have cosine theta x, which is the cosine of the angle made by that vector with respect to x-axis, and I have cosine theta y, which is the cosine of the angle made by that vector with respect to y-axis, and these are called as the direction cosines. So direction cosines are indicative of the unit vector in that particular direction. In other words, now check this out. I'm going to go a step further. I will rewrite this equation L as cosine theta xi plus cosine theta y j, and OP, and we just saw a minute ago, I can rewrite OP as L times n hat, where L is the magnitude, L is the magnitude, and n is the unit vector, unit vector. So comparing the left side and right side, you can easily deduce that the unit vector is nothing but cosine of theta x I plus cosine theta y j. So believe it or not, this is an extremely powerful result. Where is this applicable? Consider that you have a manipulator. Say, imagine a case, you have a spherical joint. So spherical, we talked about the spherical or ball joint. So you have a spherical joint. And now you have a manipulator which is somewhere here. The length of the manipulator is L. And what I want to do is, I want to find out the position of point P. which is sort of the end effector with respect to O. If I want to find out the position of point P with respect to O, I can just find out, and this is extremely important, I can just find out the angles made by this manipulator with respect to my reference coordinate frame. So, and we will talk about the coordinate frames in just a second. So what I will do is, I'm gonna find out theta x, which is the angle made with respect to theta. I'm gonna find out theta y, which is the angle made with respect to theta. And I'm gonna find out theta z, which is the angle made by that link with respect to theta. And the position vector can be written very quickly as, check this out, L in the parentheses cosine theta x I plus cosine theta y j plus cosine theta z k. And that gives you a three-dimensional position of this manipulator. And believe it or not, if you have a serial manipulator that can be moved in the three-dimensional plane, you can keep on adding to it. So you can add one more link to it. You can add another link to it. And you can actually solve the position equations for the serial manipulator using this technique. Now, one thing I want to be very careful is, when we study robotics, we are not going to study just single links. There will be multiple links. There will be multiple joints. Those joints will be either revolute or prismatic or spherical, or combination of revolute and prismatic together. So we will be studying these different positions or representation positions using matrix representation. So I want you to understand, what is this matrix representation? Matrix representation is nothing but rewriting the equations in a matrix form. So first of all, let me tell you what a vector is. So vector, it could be a row vector. This is called as the row vector. And the example of a row vector is maybe 3, 5, 6. Or it could be a column vector. We just said I, J, K. So you could have a row vector or you could have a column vector. Now, when you have two or more vectors stacked together, what you have is you have a matrix. So the matrix would look like something like this. So this is M. And the matrix would have rows. So these are rows. And they will have columns. So a simple matrix would have this is the first row, first column, first row, second column, first row, third column. So when I say A, 1, 1, this indicates row and this indicates column position. Then you could have A, second row, first column, second row, second column, second row, third column. You could have A, third row, first column, third row, second column, third row, third column. So this is a vector. I mean, if you think about it, like you have this vector stacked on top of this vector, stacked on top of this vector. So three vectors together is a matrix. Now, where M is typically represented to indicate number of rows, and N is typically represented to indicate number of columns. If M is equal to N, which means number of rows is equal to number of columns, you have a square matrix. And then most of you might have studied the linear algebra, some basic linear algebra. We can perform some algebraic manipulations and try to solve equations using matrix manipulation. So in the robotics, we can use matrices to represent point in space. So a particular point in three-dimensional space. We can use matrices to represent lines or vectors. If you want to represent objects, say for an example, an end effector or a link, you can still use matrices. Matrices can also be used to define the coordinate frames and their transformations. So going from one frame to other frame. And what I want to do is, before I go any further, I just want to give you a quick overview of something very interesting, that what are the applications of matrices. So think about, if you have a matrix M, and to be on the safer side, let me just make this matrix a 2 by 2 matrix. So I have A11, A12, A21, A22. And you have another matrix which is N, and I'm going to call this B11, B12, B21, B22. If I want to multiply matrix M multiplied by matrix N, please note M is a 2 by 2 matrix, N is a 2 by 2 matrix. For matrix multiplication, number of columns of M should be equal to number of rows of N. So unless these numbers are same, the matrix multiplication cannot be performed. So how do we perform the matrix multiplication? So what I'm going to do is, I'm going to take the first row of M and multiply with the first column of N. So check this out. When I perform the matrix multiplication, that's going to look like A11, B11 plus A12, B21. This is going to be the first row, first column of the multiplication. How would the second column look like? In that case, I'm going to take first row, second column. So check this out. This is the first row. This is the second column. So I'm going to do A11 multiplied by B12 plus A12 B22. Now the next thing is multiplying for second row, first column. This becomes A21 B11 plus A22 B21. And then we are left with the last one, which is A21 B12 plus A22 B22. So this is how a matrix multiplication can be carried out. Now the next thing I just want to tell you is the concept inverse of a matrix. Now think about something like this. Let me give you a scalar example. So this is called as a scalar example. Scalar example is 5 apples is equal to $10. So to find out the price of an apple, what I do is I do something like this: 5 inverse 10, which is nothing but 10 divided by 5 and is equal to 2. Now let me take a matrix vector example. So I'm gonna say vector matrix example. So in the vector matrix example, 5 apples plus 3 oranges is equal to $15. 3 apples plus 6 oranges is equal to $20. So how do I solve this equation now? What I'm going to do is I'm going to represent apples as A, oranges as O. Apples as A, oranges as O. And I will write this equation something like this: 5A plus 3O is equal to 15. This is not 30, this is an O. So 3A plus 6O is equal to 20. Now I can rewrite this equation in terms of the vector matrix algebra. So cut. So 5A plus 3O, 3A plus 6O. So 5, and then I will have A and O. 5A plus 3 oranges plus 3 apples, 6 oranges is equal to, now I have 15 and 20. So the expression is now expressed as a matrix and a vector expression. And this is a classic way of writing AX is equal to B, where B is a vector that is known, A is a matrix that is known, and X is a vector that is unknown. Just like the previous scalar example, what I'm going to do is I'm pre-multiply left-hand side and right-hand side by A inverse. So I would do A inverse times A X is equal to A inverse times B. Now this inverse multiplied by A gives me an identity. So I have X is equal to A inverse B. So X is equal to A inverse B. So which means if somehow I could find out this inverse, this is called as the inverse, then if I could find out this inverse, I would multiply this matrix inverse. And please note, inverse is only possible for a square matrix. The true inverse is possible only for square matrix. I should be able to find out the value of X. This A inverse is known, if this B is known, I can find out X. And what is X? X is nothing but price of an apple and price of orange. So with this, I should be able to find out the value of single apple, how much does it cost, and how much a single orange cost. So this is the simple application of matrix algebra. So let me give you some typical applications of matrix algebra. For example, if you have a point in space, that can be represented as P is equal to AX I plus BY J plus CZ K. And I don't know if you can notice this. CZ is the distance in the Z direction, AX is the distance in A direction, and BY is the distance in Y direction. So once you know I's, J's, and K's are nothing but the unit vectors, you can represent a position of point P by means of the travel in the direction of that unit vector. So this actually is the magnitude, and this is the unit vector. So I is the unit vector in X direction, J is the unit vector in Y direction, and K is the unit vector in Z direction. Please note that this is a right-hand coordinate system. So what do I mean by right-hand coordinate system? If you think about your right hand, so this is your thumb, and I just show you one more. So this is the middle finger. So this is your thumb, first finger or pointer, and this is your middle finger. This triad actually is forming the right hand coordinate system. So think about it like, I'm going to show you a slightly different orientation. Think about this as the thumb. This is the first finger. This is your pointer. And this is your hand. So this is X, Y, and Z. So if you are watching this on Sync or via Zoom, I want you to do this exercise. Just curl your fingers and have your right hand fingers, have your thumb, the first finger and the second finger perpendicular to each other. If your thumb is X and if your first finger or pointer is Y, then your middle finger is going to be Z. Always remember this. And the one way to remember this is if you have a graph paper, and if you align your thumb to the X of graph paper, your pointer will get aligned to the Y axis. And naturally, the third triad, that is Z, will be coming out of the board. And please that this coordinate system is called as the right hand coordinate system. one thing I just want to tell you is, say, we talk about the orientations. So the triad that I have shown here, you have X, Y, and Z. Now consider the rotation. If you consider this rotation, whether this rotation is positive or negative, to do that, to decide whether the rotation is positive or negative, curl your fingers in the direction of the rotation. And you will notice that your thumb, so if you see, if you curl your fingers, then you will notice that your thumb is pointing towards uh, the same direction as X. So your thumb is in the same direction as X, but your fingers are curled in the direction of the rotation. So in that case, this theta X is positive. Always remember this. To find whether the theta is positive, whether to find out the moment is positive, always use right hand thumb rule. Curl your fingers in the direction of rotation. If your thumb is pointing in the same direction as positive axis, in this case positive X axis, your rotation is positive. So here this theta Y is going to be positive because you curl your fingers in the direction of theta Y, and you will notice that your thumb will be pointing towards positive Y direction. If you curl your fingers about the rotation theta Z, you will notice your thumb will be pointing towards Z direction. So this is positive. So we will follow this convention, right hand coordinate system, whenever we solve the problems related to kinematics. Now, next is a vector can be represented by means of coordinates of the head and the tail. So for an example, this is the point, and for the sake of discussion, let me say this point is 1, 2, 3. So the coordinate of this point is 1, 2, 3, and coordinate of this point is 3, 4, 5. So I can write this vector as something like this. So I can say Bx, this is Bx, this is By, this is Bz, this is Ax, Ay, Az. So I can write this vector as 3 minus 1 I plus 4 minus 2 j plus 5 minus 3 k. So that is how this vector can be represented. But recognize that this vector is not a unit vector because it has a magnitude which is not equal to 1. But you can represent unit vector something like this. However, if you divide this vector PAB, this vector by the magnitude of PAB, you will get a unit vector in PAB direction. So unit vector, I'm going to call it P hat. So this indicates the direction. And that's what he is saying about the scale factor. So if you have a scale factor, if your scale factor is set is equal to the magnitude, you have a unit vector. But sometimes what you want to do is you want to maybe have a scale factor which would magnify the amplitude of the vector. So you could have a magnitude maybe needs to be magnified. So you can have a scale factor which is different. Now let's talk about different frames that we encounter when we study robotics. First and foremost, I want you to understand there is something called as the base coordinate frame. Base coordinate frame, also called as inertial or fixed coordinate frame. So the base, or also sometimes also called as the world coordinate frame. So this frame is fixed to the base, and this frame does not rotate. So this frame is fixed and this frame does not rotate. So that's why it is called as the fixed or inertial coordinate frame or the world coordinate frame. So I'm gonna show that this frame is fixed. So this frame is fixed. Now, if you look at this manipulator has rotation about Z. It also has this. So this is link number 1. Let me show you. This is link number 1. This is link number 2. This is link number 3. And then you have an end effector. So you could have additional frames somewhere over here. You could have one frame over here, one frame over here, one frame over here. You could have one frame over here. You could have one frame over here. So you could have, and you could have one frame over here. You could have one frame over here, and you could have one frame over here. So you could have different coordinate frames. But at the end of the day, what we want to do is we want to represent all the positions and orientations with respect to the base coordinate frame. So this is the base frame. We want to find out the orientation and position with respect to the base coordinate frame. And how we do that is the matter of our representation. We can use different types of kinematic variables. We can use homogeneous transformations. We can use unit vectors. You can use action angle. You can use screw theory. But at the end of the day, what we want to do is we want to find out from kinematics point of view, the position of all the points in this robot with respect to the base frame. So this is what is being discussed in this slide, wherein what you have is you have a point P here, and you have this point O. And what I want to do is I want to represent the orientation and position. Now this is very important. So I'm trying to represent orientation and position of P. And that is achieved by means of a matrix. And at this point, I want you to think about this matrix as something like this. This matrix is a 4 by 4 matrix. In this 4 by 4 matrix, the last row will always have zeros and ones. This subsection of the matrix has the orientation information or the rotation information. I'm going to call this R. this vector, so this matrix, 3 by 3 matrix, indicates the rotation. This 3 by 1 vector indicates the position. This is rotation. Now, what is this nx, ny, nz, ox, oy, oz, and ax, ay, and az? These are nothing but the direction cosines of that particular vector. So, and we will talk about it in just a second, but I want you to understand the representation. Any questions? The representation is a 4 by 4 matrix, and this 4 by 4 matrix has a rotation component and has a translational or positional component. And now what I'm going to do is I'm going to spend some time in trying to look at the rotations. So, and I will give you a very simple approach to look at the orientations. And this material is super important. So I'm going to write this down here. Important. So please pay attention. Consider that we have a frame or we have a coordinate system. I'm going to call this x0, y0. And this is obviously z0. So we have x, y, and z. Please note that this is a right-hand coordinate system. And what I'm going to do is I'm going to indicate the unit vectors in x direction is x I naught, j naught, and k naught. So these are the unit vectors. Now what I'm going to do is I'm going to rotate this frame something like this. So I'm going to rotate this with maybe angle theta. So check this out. This whole thing got rotated by angle theta. This whole thing got rotated by angle theta. So this is going to be x1, y1, and please note the rotation was about z. So z1 and z0 is the same. So rotation theta about z. So z0 and z1 coincide. Now what I want to do is, let me rewrite the new unit vectors I1, J1, and K1. Please note K0 and K1, they are in the same direction because Z0 and Z1 coincide. So K1 and K0 coincide. What I want to do is I want to find out the projections. So I'm going to drop vertical lines. So check this out. I drop a vertical line here. I drop another vertical line over here. So I naught, and please note, I naught is equal to, check this out, this component, which is I1 cosine theta, plus this component, which is J1 sine theta. Everybody with me so far? I1 is nothing but this I naught. I naught can be represented in terms of I1 and J1. So this will become cosine theta I1. But check this out. I need to be consistent with the direction. So this vector, since x1 is the resultant, I will have my vector arrows as shown here. So direction I1 cosine theta 1 is in the same direction as I0. So I will have a positive sign. But if you look at this vector, which is j1 sine theta, that will become minus sine theta j1. Everybody with me so far? So this I0, you would have a cosine component of I1 and negative sine component of j1, that will become the I0. Similarly, I can write j0 is equal to, now check this out. I have I1 sine of theta 1. So sine theta I1 plus cosine theta G1. So what it means is I have represented this old coordinate frame. So my old coordinate frame is x0, y0, z0 to new coordinate frame, which is x1, y1, z1 with this transformation. So I can write this and check this out. K0 is equal to K1. This equation is super important. And before I begin the next part, I just want to make sure that everyone understood what I have written over here. So these three equations, I just want to make sure that everyone understood. Any questions with these equations?
Professor, can you say it again why we have negative sine theta J1 on the first?
Yes, because look at this arrow. So this is J1. The sine component is this. And look at the arrows that I have drawn. So you need to go up and in this direction. And if you look at the arrow, this arrow, which is here, is opposite of this direction here. That's why you have the negative sign.
So we're using the I1 and J1, but why don't we use the cosine side of the X1?
Cosine. So we are interested in finding out the relationship between I0, J0, and K0 with I1, J1, and K1. So what we need to do is, if you look at the I0 direction is this direction. On I0 direction, you have this I1 cosine theta and you have J1 sine theta, where I1 cosine theta is in the positive direction, J1 sine theta is in the negative direction. That's why you get the first equation.
Okay.
On the other,
I understood. Thank you.
okay. On the other hand, if you look at the y direction, you have J1 cosine theta. This is J1 cosine theta. And you have I1 sine theta. Both of them are in the same direction as J0. That's why you have the positive sign. This equation, now it will be clear in just a second, can be written as I naught J naught K naught is equal to cosine theta sine theta minus sine theta cosine theta 0 0 0 0 1. Are you with me so far? This is a very, very important equation. Now there is a trick to it. So now what I want to do is, I want you to, how do you don't have to remember this matrix at all. So what I want you to remember is something like this. Consider this is projection off and this is projection on. So I'm interested, and I'm going to rewrite this. I'm interested in finding out projection of x1, y1, z1 on x1, sorry, x0, y0, z0. Now I want you to understand what's going on here. I just derived the equation mathematically, but I want to give you a very simple intuitive understanding of this. This is the frame, new frame. This is the new frame. This is the old frame. I'm interested in finding out the orientation of, or the projection of the new frame onto old frame. Now everyone, please pay attention. Check this out. Projection of x1. Can you, okay. I want everyone to look here. This is my x1. Projection of x1 onto x0 is what? Cosine theta. Do you agree with me?
Yes.
Projection of x1 onto y0. Projection of x1 onto y0. Projection of x1 onto y0 is what? Sine theta. Just check this out. Look at x1 and look at y0. Y0 is here. X1 is here. And projection of x1 on z0, nothing. There is no projection. So 0. Let's look at projection of y1. Projection of y1 onto x0. Projection of y1 onto x0 is minus sine theta. Projection of y1 onto y0 is cosine theta. And projection of y1 onto z0 is clearly 0. Next thing, projection of z1 onto x0 is 0. Projection of z1 onto y0 is 0. But projection of z1 on z0 is 1. And I'm going to solve this again. So everyone, please pay attention once again, because this is what we will do again and again when we try to solve the kinematic equations. So what I'm trying to do is this. I have an old frame. Just a second, let me finish this and I'll answer your question. I have an old frame. I have a new frame. Old frame is x0, y0. New frame is x1, y1, and z0 and z1, they coincide. This is theta, this is theta. I'm gonna draw perpendiculars and the rotation matrix, projection of projection on. The new frame is x1, y1, z1, x0, y0, z0. Check this out. Projection of x1 onto x0 is this guy, which is cosine theta. Projection of x1 onto y0, projection of x1 onto y0 is nothing but this guy, which is sine theta. Then you have 0. Projection of y1 onto y1 onto y0 is cosine theta. Projection of y1 onto x0 is minus sine theta. 0, 0, 0, 1. And this is how you will find out the projection matrices. I got one question. Yes, I will be uploading the lecture notes, but it's 5:45 and we will stop here. But look at this material, and if you have any questions, I would be happy to answer.
Is the projection of Z1 and Z not 0 because it's on the
It's
Z
1.
axis, or is it always like that?
Because Z does not have projection on X or Y, because if the rotation is about Z, so Z1 and Z are coincident. So that's why there is no projection.
Okay, so because they share the same projection, then that's why the 0.
No, they are one and the same axis.
I see. Thank you.
The rotation is about